Okay. So while we do have the exam coming up and the others, and we have the exam coming up, we have this Josephus problem coming up. The only time that, or solitaire. Unfortunately, the only time for me to discuss this Newton upcoming assignment is now. So I'm going to do so now. So it's going to be a fun discussion. Just bear with me. Don't panic if you haven't gotten finished with this. Just this is kind of a thing to refer to back to. This is one of those. Most of the assignments, I'll admit, I actually steal. You may have seen multiple times I give credit for the assignment somewhere else. This is because I personally am a big believer of if it ain't broke, don't fix it. SIGC is Special Interest Group in Computer Science Education. It's one of the big research journals, big research conferences for computer science education. Every year they have a panel called Nifty Assignments, which I have to go through, and I go through and check for new ones every so often. And I've grabbed various ones from here, like if you've been in 1051 with me, you probably remember the Hurricane Tracker. The Fox and Rabbit came from here. A bunch of the solitaire encryption one came from here, although I was familiar with the solitaire encryption from having read Cryptonomicon. So there's a lot of nifty stuff here, which is why it pleases me to say this the stack and queue assignment, or just rather the stack assignment, has no origins whatsoever. That was completely me. So I'm that's a way of saying I'm a bit proud of it. So what is the stack and queue assignment? What we're going to specifically be going over is stacks. Now, typically in a lot of curriculum, the curriculum simply goes: we are going to do arrays, then we're going to do stacks, then we're going to do lists. Stacks and queues and lists. Because stacks and queues are just simple versions of linked lists. And I think that's it makes sense, but it's not optimal in terms of teaching speed, because you're going to still be expending the same amount of effort on linked lists, but now you have to spend additional effort on teaching stacks and queues. Whereas if I teach linked lists first, I get to teach stacks like this. Stacks are just lists, except you can only operate on index 0. That is it. That is it. There you go. One sentence. That is a stack. So all you can do is add to the front of the stack, or rather we call it the top of a stack, or remove from the top of the stack. You can also obviously look at it and see what it is, but that's it. We call those operations alliteratively push on the top of the stack, pop, and peek. That's it. Push, pop, peek. We call it there's also another fancy term for it, which is first in, last out, because the first thing you put into a stack is going to be pushed all the way to the bottom, and then it's going to be the last thing out. So it's a list where the functionality has been shrunk down, where basically there's not nearly as much functionality. Why? Because sometimes it's useful to for the sake of doing stuff, to limit how you're looking at something. If you want to use a stack in Python, by the way, what you do is that you will basically be what is it? Oh yeah, you basically, they have those indexes. They just work on the end of the list instead of the beginning of the list. That's just aesthetics, right? That's just like a kind of a difference of opinion for construction. But it's either all operating on the beginning or all operating on the end. You choose which one. On the other hand, a queue is what we call a queue in. On the other hand, a queue is basically the same thing, a limited data structure, only it represents a line, a queue, right? Now, so a queue, right, in case you're not familiar, Q-U-E-U-E, right? And again, so the way you pronounce Q, as I like to joke, is that you say the first letter and just ignore everything else. But it is A line, right? It is when you are waiting in line and waiting your turn for something. So the first thing in the queue is the first thing to go out. This is typically used for buffering stuff, right? So when we're processing one piece of data at the time and we're processing it in a sequential manner, or if people are waiting their turn for something, or simulating something being waited. So when you program and write pseudocode and work here at university, so this is actually new material that I've not done any year. When you are working here at university, you will use stacks and queues all the time. In industry, you will not be doing that, or you might be doing that, but that is not the optimal choice. Instead, what you will want to use if you're doing Java is the deque, which is spelled D-E-Q-U-E, which basically allows you to do insertion and removal at both ends. It means double-ended queue. And the reason being is that, let's see, it extends the queue interface. When it's used as a queue, you get first in, first out behavior. It can also be used as a stack. And here's the important bit. This interface should be used in preference to the legacy stack class. When the deque is used as a stack, elements are pushed or popped from the beginning of the queue. Stack methods are, and here's the equivalent it says. And this just simply has to do with basically it being a much more up-to-date class with much more safe handling procedures. It can go into that. Like if you look into, I'm in the middle of writing a textbook and I had to dive into this as to what actually, like, because as part of that, I like to say, here's what we do, here's what I'm teaching you, but here's what actually happens, right? Right here, it's because, right, so notice, if you notice a stack in Java, which you can, please feel free to use it. I'm not saying don't use it, because what matters is the problem-solving ideas that you get from using this. It extends vector. This is a class I've never used, even though it's been in Java since 1.0. Yeah, as of Java 2, 1.2. So Java version 2 is actually 1.2. Java's version 6 is 1.6. So they eventually just changed it to whole numbers eventually. It was retrofitted to work like a list. And then if a thread-safe implementation is not needed, it is recommended to use a list instead of vector. It has all these things about threading versus non-threading that you really don't want to have to think about. So, anyway. So yeah, a more complete and consistent stack of LIFO operations is provided by the deque class and its implementation, which should be used in preference to this class. So there you go. So feel free to, please, I'm expecting you to use the stack class. If for some reason you write on an exam that you are using deque, guess what? No worries. Again, I'm the kind of person who really cares as long as you're answering the questions and following the rules specifically laid out on that question. If it's not explicitly prohibited, it is allowed, right? So, all right, so with that, let's get, again, the stacking queue is fairly straightforward. It's great practice if you need to help on that. Yes?
So, just to make sure, deques are more used for industry when they...
Yeah, if you're actually going to be doing that, if you would actually be doing that, I would assume you'd be using it in industry. Or rather, if they know what they're doing, they should be using a deque, is what I'm saying. But that's just simply because it's better. Yes?
Will this be on the exam, or is it only up to linked lists?
The exam is only onto linked lists. That is a great question. Exam is only onto linked lists. The part of this is that the material just must keep going, otherwise. But fortunately, this one's a fun one, because what this is that you have 3 classes here. A maze, and I go through them in the PDF, and I actually do have, I think, a video where I go into this in more detail. And you do have another opportunity for extra credit here, so I just figured I'd go into this. Because, believe it or not, oh, really? I didn't upload the new one where I corrected the typo. Anyway, believe it or not, this assignment is, this is the answer. I give you the answer in pseudocode right here. This is the answer, okay? So it's just a matter of, again, seeing an algorithm and then like being able to interpret this. What you're doing here, if you know the term, is that you're going to be implementing def first search. And what you are doing, so that is the goal, the abstract goal, the teaching goal. The actual like goal of the assignment is that you are making something called again, it's two things. It's making a code that solves a maze. So given it will randomly generate a maze and it will solve it for you. The other thing it will do is that, again, you're being given a bunch of unfamiliar code, and I just want you to get to being able to get used to, oh, here's a bunch of code, here's where I know to modify, and so I just kind of work around everything else that I don't know, or I learn it. Or I see if there are tools provided for me. So you have three classes. You have the maze class, which is the class that you will primarily be using. That's your runner class. That's your main class. That's what you use to run the program. You have the maze grid panel. That's where you're going to be doing most of your work. And then you have the cell class, which is the individual squares of a maze. Okay? No. What? Int? Okay, I typed in int, and what did it do? It gave me Microsoft.
It does that when you type too many letters for some reason.
Int.
It does that on my computer too.
See? Just like that?
Yeah.
Go home, Windows. You're drunk. There's this old Garfield comic that I'm particularly fond of, where John talks to Garfield about, and this is like in the 1990s, about how AI is going to be the new, artificial intelligence is going to be the new big thing. And Garfield then snatches his, the lasagna out from under him and says, oh, wake me when they come up with artificial cunning. And yeah, I love that. I love that one. Let's go ahead and, you know what, we can just simply... Okay. Right, I'm in full screen mode, appearance. So one of the things you can do is there's all these distraction-free modes, these Zen-free modes, which are really useful. You just got to remember sometimes, oh, I'm in that mode. So we're just going to drag, once again, what we do is that we drag these things. If you're working in IDE or anything, you drag it into the folder that your project folder. In most of our IDEs, that's going to be, SRC. If you're working in VS Code, that's whatever you personally set up for yourself, okay, or whatever the configuration is. So here's our maze, very simple. We run it, okay, and all this does is that it creates this creates a frame. So this is using basically some really old legacy stuff because that's what I learned how to use for graphics. There's probably a much more updated version of this, but what this does is that this creates the literal window that the program exists in. It creates the bar, the thing with the X with the big X to close it, and this bar that I can drag. It specifies that, hey, it's going to be 800 by 800. And then the way a frame works is that a frame has a panel inside of it, or it can hold a panel because it's a window. So you put a panel in the window. I know. And it's all metaphors. Okay, so you add the panel, and I created my own panel, which extends the base panel, right, the one that's provided, and it's called a maze grid panel. Why? Because it is a grid panel, which is a type of panel, and it's used for mazes. And I simply declaring that this is a 5x5 maze, meaning that it's made up of 25 cells. It's 5x5. Right, here's your internal class, right? And then here's your extra credit, generation, homework, solve maze. Public Boolean visited. This is going to be useful for us. That tells you whether we've been to a square or not. And then this is my code to generate a very basic maze for you, right? You want to the extra credit here is basically generating a much more complicated maze. Okay, so the goal is you want to write an algorithm that gets from here to here. How? So let's go ahead and learn a bit of Greek mythology, actually. So once upon a time in Greek mythology, there was a son of Zeus named Minos, and he was all around a pretty terrible dude. A lot of people in Greek mythology are, but this guy was particularly terrible. And because he was so terrible, he ended up with a half bull man for a son because let's just say that a lot of the time punishing the dude meant actually punishing the dude's wife. So, because that's the way old myths worked, because everybody's terrible. So now this bull man was basically put into the labyrinth, capital L labyrinth, big maze thing built by Daedalus, the kind of inventor of all Greek mythology, and every so often, basically, Minos would extort the Athenians to provide him with men and women to be devoured by the Minotaur. A son of Poseidon, which one was it? Theseus, right? Theseus put an end to it. The Greek gods had lots of children. They were definitely not the paragons of fidelity, except for Hera, because that's literally was her job. So the way it worked for him is that he didn't just simply overpower the Minotaur. In fact, if we look at some Greek art, like Labyrinth. My son's also going through Percy Jackson, so I'm relearning all this stuff. But I'm a pretty big buff on when it comes to mythology, right? The Labyrinth was kind of like not one of those fun mazes, but one of those it's all everywhere and I can't tell where I am kind of mazes, right? Because everything looks the same. Let's see. Here's a good one, right? Here, Theseus, in case everybody, because we need to label who he is. And we can see Theseus there. Some version of the myth have him with a sword. Some don't, right? So let's look at how he did this. So he's a demigod. He doesn't really need the sword, or does he, depending on the story. It really, they're pretty, in physical combat, these guys are pretty resourceful. What he does have is right here, gotta love that, the level of detail that, Google did the art scans with, is that. And that is Ariadne's thread. Ariadne was basically the non-jerk of the story. She was Minos' daughter and was pretty cool and was infatuated with Theseus. And she gave him this spool of thread. And what he did, in order to figure out, basically to not get lost in the labyrinth and get exhausted, was he just simply unspooled this thread to figure out where he was. And then he would use that thread to go backwards. Now, to make sure you don't go down the same path, this is where having the sword actually comes in. Okay, the sword comes in handy because rather than using it to slay the Minotaur, if you have to backtrack by winding the thread back up, right? What you can do then is that you can mark the passages with the sword to say, I've gone down this passage, I don't want to go down it again. Okay? So basically, thread and sword. Use the thread to basically say, this is where I need to back up to. Use the sword to say, this is a dead end, I don't want to go down this path anymore. You can do the same thing with chalk, which is what we're going to be doing, basically using color coding to say, this is a path I want to go back on, and go forward. So Minos, so anyway, Theseus killed the Minotaur, and everyone did not live happily ever after, because people rarely do in mythologies. Minos eventually died in a bizarre series of events involving him being a stalker, a seashell, and even more thread. Greek mythology is wild. So anyway, how does this work? Well, maze solving, in other words, has been kind of one of those things that has been around for a while, and I like to talk about that. We are going to go back to the Theseus strategy, which is called depth first search in a bit. But the other way, but if you need an easy way to go through a maze and you do not have thread, most mazes, the entrance and exit exist on the same quote-unquote wall, right? They might not be a wall like this, but they exist on the same surface. In other words, you could draw a physical line along the walls and eventually hit the exit, right? The exception is like if there's an elevator in the middle or something like that, and that's what you're trying to get to. So if that's the case, you can follow what's called the right-hand rule, which is very simple. You just slap your hand to the right to the wall with your right hand and just don't let go. I mean, I did, but you get the idea, right? You just simply follow that and be very dumb. It's a very, very solid, good strategy for solving a lot of mazes. A lot of mazes. So
next time you go to a corn maze, you already know the cheat to get through it.
It's one of those. I mean, you're probably going to go have a lot of wasted space, but it works. It works. In fact, having fun with basic robots is one of the things you can make them do, which is solve mazes. There's other ways to do it. Dead end filling. The recursive algorithm is basically what we're looking at, but we're doing it without recursion. We're doing what's called, we're doing depth first search. The idea here behind depth first search is that we're going to use colors. We can change the color of whatever square we're on in this, okay? And instead of thread, we're going to be using a stack. The stack is our thread. Basically what we do is that we add, when we travel into a square, we add it to our stack. We push it into our stack. Basically, and because it's the stack, again, is you only operate on the top of the stack, you know if you need to go backwards, you just look at the top of the stack and go there, and then remove it from the top of the stack. Make sense? And then if you have to go back from there, you just look at the top again and remove that, right? So you can see how that's very easy. By limiting, we don't have to do much. By limiting the operations, we don't have to do much thinking. So at the beginning, obviously, what we do is we create the stack. I define the start. The start is always going to be the top left corner. The end is always going to be the bottom right corner. And I set those to be green and red. And then I just start that by pushing it onto the stack. So your main loop is going to say, while this is not done, the code is very simple. While this is not done, and the stack isn't empty, basically you didn't hit a dead end and you didn't finish, we get our current position by looking at the top of the stack. The top of the stack is going to represent where we are, and because we're done, we're just going to look at the top of the stack to figure out where that is, rather than trying to hold that in a variable. And what we do is that we ask for each of the cardinal directions, can I go that way? How do I know if I can go that way? I can go that way if I can physically move there, and I haven't visited there yet. What do I mean by physically going there? Well, there's walls, right? So if there's a wall in the way, I can't go there. So basically, if there's a wall, as long as there's not a wall in the way, and I haven't been there, which I'll discuss in a second, then I'm going to try to travel there. If I can't go north, I'm going to try south. If I can't try south, I'm going to try east. If I can't try east, I'm going to go west. And if I can't go in any of those directions, guess what? I'm in a dead end. Okay, so I'm going to backtrack in that case, right? And that's the entire algorithm. And you backtrack by popping. So that's the entire algorithm. That's it. Basically, you're making a local decision every time. You're not trying to come up with a global strategy of big braining the entire maze. You're just simply saying, I'm here now. Let me look around me and make my position, my decision off of that. Okay. So how do I tell whether something's been visited or not? The answer is I use the visited function, which given a row and column will get the cell that corresponds to that, okay? And a cell does know its own row and column, and you basically ask, hey, what color are you? By using c.getBackground, right? Ask the cell to get its background. I've already written something that does this for you. I'm just showing you how it works. And then my code treats anything that's white or red. Why red? Because the end square is red. Anything that's white or red is an unvisited square. Make sense? So if it's this color, then great. And that means that you can use any other color you want to mark your squares. Okay? Now, how do you tell if you can physically move somewhere or not? I made this fairly easy to figure out. Every cell has, by default, 4 walls, and it has those walls set up to be true. Every cell has one of those 4 walls, and your north wall is going to be somebody else's south wall. And I just make sure that whenever I remove a north wall when I'm generating the maze, I also remove the respective south wall, right, so that you can travel through them. And that's basically it. I just simply you have these Booleans, and you can just query whether they're true or not to check if there is a. So if you want to go north, you ask, hey, does the current cell I'm in have a north wall? Why is this useful? Because if you're because the way I structure the if statement, by the way, is like this. I ask, if you can go north and you haven't visited the cell to the north yet. So you can go north. You can check if you can go north simply by asking, is there a north wall? And there's a north wall along all the top of along the top of this, so you don't have to worry about going out of bounds if you check if there's a north wall first. That's the other thing. What direction is north? Right, it's that way. So in row column notation, if I'm at row comma column and I want to go north, what is the north, the square to the north of me if I'm at row comma column? So that's the thing, that's the trick. X and Y are reversed because it's row column, right? So column is column is the X direction, row is the Y direction. And furthermore, up is negative, right? So if you want to go north, you have to go row minus 1. So the reason I bring this up is over here is that if we do something like this, I'm just going to talk about this right here. If you do a check that would be sometimes it's okay to do a check that would be out of bounds over here if you eliminate the possibility that it's going to go null over here. And that's exactly what you're going to be doing. This is because Boolean statements have something called short circuiting. If this is white, if this thing evaluates to white, guess what? The compiler is optimized so that it is not going to check if it's red. That's an unnecessary step. This is an OR statement. If one thing is true, the entire thing is true, so I don't have to evaluate both of these. That's why you could do something like this. And as long as if I plus plus is equal to 2, right? That's why a statement like this is considered harmful, by the way, because it can execute in the middle of an if statement and you don't know whether or not it's going to execute, because it might not execute every time the if statement runs because of what's called short circuiting. And so now to answer a question you didn't know you had, why am I using 2 bars? Because that activates short circuiting. This is running a Boolean evaluation without short circuiting, meaning both sides of this will run every time. It's the unoptimized version of it. There you go. All right. So with that is everything I have on that except for the extra credit. So these external links, by the way, are really good. But maze generation, every maze generation algorithm has biases. My particular bias is that I don't make very good mazes. I specifically don't make very good mazes for this algorithm over here because it's very simple. I basically just flip for every square that's not along the west side or the north side. I flip a coin, and then I decide whether or not I'm removing what wall I'm removing. I either remove for every square. I decide to either remove the north wall or the west wall for every one of those squares, just randomly. And that always means that there is basically a straight line jagged path that goes through the maze. That's just simply so that the maze is easy to solve, but also it's visually easy to see what's going on. And it was easy for me to write. Maze generation algorithms, though, can use depth first search as well. Basically, what this maze generation algorithm is doing is that it's basically saying if it's an unexplored space, I'm going to choose which direction to go at random. And then when I hit a dead end, I back up and confirm that is a generated spot. So see, it's basically when it hits whenever it can make a choice at a non-dead end, it tries to go there. So if you do this depth first search style maze generation algorithm, which is the extra credit, you end up with these nice, long, windy passages. Every maze generation algorithm has a bias, and depth first search is biased towards these long, windy passages. Right, here's one with horizontal passage bias. Here is another algorithm called Prims, which basically makes a bunch of connecting sets, and it makes a lot of, as you can see, these kind of jagged kind of, it looks like it looks like a randomly generated dungeon in an RPG, almost, in my opinion. And then other ones, another maze generation algorithm is one of my favorites because it's very easy to see recursively. You split each square into space into 4 quadrants, then you make it so you can travel each of the 4 quadrants, and then you do that for and then you do that recursively for every remaining space, right? And just keep continuing. All right, so that's my spiel about this. Any questions? All right, so I'm going to go around the room. This one is not that hard. Again, follow these instructions for doing this. If you're having trouble, again, the main trouble that students have is the checking to see if you go north versus, how to basically travel north, south, east, west. My advice, by the way, is because if you try to implement this all, this is the last bit of advice. If you try to implement it like I say, which is with the while loop, you're not going to get an answer until you have the whole thing. So when you're starting off, rather than doing a while loop, do it like this. For int I is equal to 0, I is less than maybe 5 or something. I++, which means your maze will not finish. It will just simply run until there have been 5 executed steps, which means that you can now debug it. And then you can replace that for, and then when you're actually ready to see if you can get to the end, you just replace that with the while loop that you need. Okay, so that's a very common thing when you do have that kind of while loop. And you need to test something that runs. You turn that indeterminate loop into a determinate loop. Okay. Now I'll stop recording.